Hey, all right, welcome back. This is, I think, the fourth linear regression deep dive stream that we're recording, and I think this might be the last. We'll see how it goes. Next up is to get the gradient of L. So without further ado, let's get started. Okay, so to kick up where we left off after last time where we had a lot of technical difficulties, hopefully we don't have as many issues this time, we vectorized our simple linear regression model where we just have a single feature predictor, one input x, that has a coefficient of w, and we have this intercept term b. And what we did here is we took that and wrote it in matrix notation, and we found our mean square error loss function using that matrix notation as well. So W, to go back to the start here, W vector is the vector that holds our unknown coefficients that we're trying to predict being W. That's 2 by 1. That's important. We'll probably reference that again later. X is a matrix with our input features and a column of ones. So if we have n pieces of data, x is going to be n by 2 in this case. And so we can write our simple linear regression model, y of x is going to be equal to x dot w. And we found the mean square error loss function is this fella right here, w transpose dot x transpose dot x dot w minus 2y transpose dot x dot w plus y transpose times y. So if you're not sure where these things came from or how we derived this, go back and watch that deep dive stream 3 video. So this is our loss function. What we're missing here in terms of completing the whole gradient descent process to get to convergent linear regression model is what is the gradient of that big guy L. So let's go ahead and do that right now. Flip this over. One thing I want us to remember here is that big thing L is just a mean square error value. So it ends up being just a scalar. Remember, L of W is just the mean square error of our value, the mean square error, okay? So it essentially is a scalar, okay? Now, in order to take this derivative using that matrix notation, let's do a brief vector calculus refresh, which I am honestly extremely rusty on myself. Vector calculus refresh. So we want to take the derivative of L of W. That is the derivative of a scalar. So the derivative of a, let's start here. The derivative of a scalar. The derivative of a scalar, let me just say a scalar y by a vector x. So x will be a vector, a column vector, so I'm going to write it as x. It's got entries x1, x2, yada, 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 xn transpose is the derivative of y with respect to the vector x is a vector containing all the partial derivatives there. So this is going to be the derivative of y with respect to x1 in the first component, the derivative of y with respect to x2 in the second component, so on and so forth, the derivative of y with respect to xn. So that would be the derivative of y with respect to x. And the gradient is just the transpose of this. Remember, we said the gradient is essentially a column vector that contains the partials of all the independent variables. So the gradient is just the transpose of this derivative right there. Okay. So in our case, the derivative of L with respect to the vector W, the vector W, would be the derivative of L with respect to, now W, the first component of W is B, the bias term, right? So just notate that up here. Remember, W right now just has B and that second component there. So the derivative of L then with respect to the weight of the first feature there, W, right? So we're doing our prediction y hat, right, is equal to B plus W X for an individual option, for an individual predictor there. So this is the exact partial derivatives we want to calculate the gradient. Those are the exact partial derivatives we calculated before when we sort of just did this by hand by just calculating the partials individually in the second deep dive, part 2, I believe. So that's good. That's good. Okay, so it turns out that this derivative here, this gradient calculation is quite nice, and it works out as expected here. So in our case, if I look at what L of W is at the end here, the W transpose XW, all that stuff right here, this is what I care about. So let me write that over then on the other side. This constant factor 1 over n, just to clean things up rather than have to continually rewriting it, I'm just going to ignore that constant for now, and we'll add it back in at the end. And so we'll go ahead and say, what would the partial, or what would the derivative with respect to W of L be, essentially, without the 1 over n? Or what would the derivative of, in this case, it was W transpose X transpose X, W. And then we simplified it to minus 2 Y transpose dot X plus Y transpose dot Y. Okay. And so it turns out that this derivative is actually quite nice. If you want to take it, sort of just using vector calculus stuff here, you look at this, say with respect to W. If you haven't done this in a while, just imagine how would you take this derivative normally as just a regular old single variable function. And I would look at this and you say, well, I've got two W pieces here being multiplied together, so there's going to be a product rule coming into play here, right? It's going to be a product rule coming into play there. And so what we're going to end up with at the end here, let me see here. What is this going to end up being? Am I missing something here? Let me check my function on what I'm trying to take the gradient of here. Gradient of L, 2xy. I did. I forgot that W right there. My mistake. Right? Dot W. There we go. Okay. So applying the product rule here is going to leave us with 2 W transpose dot X transpose dot X. So you can think about like the derivative of the first times the second plus the first times the derivative of the second, and then we can do some combining there. And then minus 2y transpose dot x dot w, you basically just have a single piece, a single vector factor of w there, so the derivative there would just be minus 2y transpose dot x. And then this piece right here, these are essentially constant, if you will, with respect to w, so that derivative there is just going to be 0 plus a 0 vector. Right, plus a 0 vector. So one thing after we do that calculation, and I'll break that up a little bit more if it seemed a little hand-wavy for you at the moment, but if you're good with that or comfortable with that step, go ahead and take a look at the dimensions of what we have here. So 2 times W transpose, remember W is just 1 by 2, so W transpose should be, oh wait, actually, this is this is W transpose right here. W is a column vector. So that's W transpose. So W transpose is 1 by 2. And then X transpose, remember what the original vector X was, that matrix here, let's go back to the top. X is n by 2, so X transpose is 2 by n. And here you can see where we defined W originally to be that column vector. So X transpose is 2 by n. And then X is n by 2. And then, so what do we have here? We have a 1 by 2 and a 2 by n, so that's a 1 by n. And then we have that by an n by 2, so this ends up being a 1 by 2. And then 2y transpose. Y transpose is 1 by n, right? Y is the vector that holds our column vector that holds all the actual observed values. There's n of those. And then x we know is n by 2. So this works out to be 1 by 2 as well. It's really good to see these dimensions line up to do the vector subtraction. A 1 by 2 minus a 1 by 2 there. So this is the derivative with respect to W. So if we want to think about this in terms of the gradient, or think about the derivative with respect to W transpose, that is going to be the transpose of all of that. So 2W transpose dot X transpose dot X minus 2Y transpose dot X, and then that's all we have left over, and then that is a transpose. And so thinking about the transpose being distributed inside of each of these pieces here, you have that socks shoes property that we sort of talked about before. So if I kind of do this type of idea and apply it there, what are we going to be left with? How's the green look on the screen, actually? Can you see that? That's not terrible. Actually looks better on the stream than it does on my tablet. What do we have here? 2. And then reversing the order here, I'm going to end up having, if I have this transpose to be distributed inside of this product, 2x transpose dot x dot w minus 2x transpose dot y, I believe. Yep, that looks good. And so then we have 2 times x transpose dot x dot w minus x transpose dot y, right there on the right hand side. Does that look right to me? Yes. X transpose dot x dot w minus, yeah, that looks good. So that's what we have there. So the gradient, remember our gradient symbol for L, the gradient of L, the only thing that's missing is that constant factor of the 1 over n that gives us the mean square error, right? So we have a 2 out in front here, so that's 2 over times 1 over n, or 2 over n, and then times x transpose dot x dot w minus x transpose dot y. And that right there, my friends, is the gradient of L when you factor back in the 1 over n. When you put back in the 1 over n piece. Awesome. That is pretty sweet. Actually, there's one slight further simplification I will make to this that will help us in terms of thinking about coding this. And that is that we have an X transpose inside common on both of these pieces right here. So in terms of coding, we could also write this as 2 over n X transpose times, if I factor X transpose here, then all I have is x dot w minus y. And the reason that is super useful is because in terms of memory, we probably already have the quantity x dot w. Remember what x dot w is. X dot w is literally your predicted values for y. literally your predicted values, right? We're writing our equation as, right, y of x is equal to x dot w, right? That's our model. That's our prediction, right? So we're basically saying we're taking predicted values minus the observed value. Predicted values, and then this is the observed. Predicted values minus observed, x transpose times that on the left, and then scale by 2 over n. And there you go. That's awesome. Awesome, awesome, awesome. Okay. And we now know where that 2 comes from, right? That 2 comes out there. Sometimes you'll see this implemented without the 2, and it's actually just the loss function then is just the halved mean square error, half mean square error. And the only reason you would do that 1/2 is just to make it a little bit cleaner, so you have just 1 over n out in front rather than 2 over n, which seems a little bit weird. Either way is just fine, because if you are going in the direction that's going to lower the halved mean square error, it's the same thing that would lower the regular mean square error. It's just a scaling factor there. Okay, cool. So technically, that's really all you need, or all we need, and we're done, and we're pretty much good to go to walk through. And if we have this in vector form, we can extend this to multiple linear regression without much extra effort. But that's what we're going to do on our next stream is how do we start here and really convince ourselves that, well, basically all we would have to do is get to this stage, I think, and nothing else was really too hand-wavy at that point, okay? So we'll do that component by component on Thursday, and I hope to see you then.